So I like to go camping. And one of the things we do when we go camping is we burn wood to make a fire. We have a control volume around these logs. We make a fire. Now, this fire has smoke that leaves from it, and we're also having heat leave our control volume. Let's say my fire's finished, and I collected all the mass, all the smoke that left the system, and I add back just as much heat as I had at the beginning. I'm sure you would start to look at me funny if I said that this means my spent logs would go back to brand new wood. Even though in this second case, I've still conserved mass and I've conserved energy, I don't get back to my original state. The process is not reversible, even though conservation of mass and the first law say that this second process is just fine. So to describe the universe, we need some other rule to tell us what's the right direction that a process wants to move. I've been saying that there's these 3 steps that we want to do for these open system processes, and that's true if you're trying to analyze a process that you know exists. But if you're designing something that no one has ever done before, you might also want to do a second law analysis to make sure that the thing that you're trying to do is possible. To do this, we'll have to understand a little bit about a different property type called entropy. Now, what is entropy? It's always a little bit difficult to get some kind of a proper definition, but most people says it has something to do with disorder or randomness in a system, or that it captures this idea that systems have losses. What the second law tells us is that unlike mass and unlike energy, entropy is not conserved. The total entropy in the universe can never decrease. So there's always losses each time we have an energy transaction. So these losses we call irreversibilities. They're things that are dissipating useful energy. In thermodynamics, we have this concept of a reversible process. Think about a pendulum. If you pull a pendulum back and you let it go, because there's friction in the system, every swing of that pendulum, even though the frequency stays the same, the amplitude will gradually get smaller and smaller until the pendulum stops moving. That process is not reversible because you have your starting position, you let the pendulum go, and it doesn't come back up to where you started. So ideal processes are processes that are reversible. The best you can ever do is have this reversible process where no entropy is generated. Your entropy generation rate would be 0. An irreversible process, or a real process, is one in which entropy is generated where we can never hope to get back to our initial position without putting more energy into the system. Now here we have an elapsed time version of the second law. Here we have the change in entropy in the system is equal to the entropy that comes into the system from heat transfer plus the net entropy coming in with mass, plus this other term here that tells us about the entropy produced within the control volume because of these irreversibilities. This is different than conservation of mass and conservation of energy because here entropy is not conserved. We're always making more no matter what we do. So when we look at the second law, we know that we violate the second law if that entropy generation term is negative. And actually we violate the second law if the entropy generation term is 0, because that's sort of the limit of what we can do, but we can never achieve that 0 entropy generation. We can look at the elapsed time version of this equation, but like some other equations, we can divide by delta t, take the limit as it goes to 0, and we'll get the rate version of this equation. Here we have the rate that entropy is being stored or depleted in the system is equal to the rate that entropy enters the system by heat transfer plus the net rate that entropy enters by mass flow, plus now this entropy generation rate. And just like the elapsed time version, we need to be creating entropy, so the entropy generation rate must be positive. The limit case is when the entropy generation rate is 0. That's the best we could ever hope to do, and we can't even hope to do that, but we maybe could approach it. And if the entropy generation rate is negative, we cannot do this process. It's not possible. So now I've been holding out on you. We've been drawing these TV diagrams up until this point. And it's always a little hard for me to draw these diagrams because I know that what we want to be drawing here is the TS diagram. But when we didn't know about entropy, it didn't make sense to do that. So from now on, when we draw these graphs, not a PV diagram, that's going to stay the same. But when we draw these graphs, it will be a TS diagram. Now this follows all the same general rules as a TV diagram. It's just now we have entropy, or a specific entropy, on the x-axis. Let's look at some cases where we would apply the second law. It's worth pointing out we'll start by looking at turbines and pumps, because in turbines and pumps, we tend to assume that they are adiabatic, which means we get rid of this heat transfer term, and that's the one that's going to cause us the most trouble if it sticks around. Here we say the system is at steady state. This turbine has one inlet and one outlet. It's adiabatic. And if it's ideal, the entropy generation rate goes to 0. In this case, as long as the mass flow rate is not 0, we have an inlet and outlet entropy that are the same. If the entropy doesn't change, this process is called isentropic. If I look at a real turbine, I make almost the same assumptions. Steady state, one inlet, one outlet, adiabatic. But now I can't cross out the entropy generation rate term. And here I see that the outlet specific entropy must be bigger than the inlet because I'm generating entropy in my system. Entropy increases. So if I wanted to draw these two processes, the ideal turbine and the real turbine, on a TS diagram, what I would see for the ideal turbine, I'm lowering the pressure, but I'm keeping the entropy the same. So I have this vertical line downward. For these isentropic processes, we write them as the state number and then an S to remember that they're isentropic. If my process is real, I have a real turbine, then the entropy increases and my process line goes down and to the right. What about a pump? Pumps are almost the same as turbines, at least from a first law and a second law perspective. They're steady state, one inlet, one outlet, adiabatic, and in this case, ideal. So that entropy generation term goes away. And again, I have this isentropic process. And just like the real turbine, the real pump shows me, after I do this analysis, that the entropy in the system is increasing. So if I want to draw a pump, I start with my inlet. My ideal pump is a vertically upward line on a TS diagram. And my real pump goes up and to the right. So, like I said, it's a little more straightforward when we can cancel out this heat transfer term, but things do get a little more complicated when the heat transfer term sticks around. And we'll look at a couple cases where that happens next time. Thanks for joining me on Thermo Shorts.